Welcome back to the course on architectural design of ICs. So, in the last class what we have seen that control 2's complementary circuit and then sum of n natural numbers. Initially we have done, that means we have the sequential circuit of that means sequential implementation circuit for n natural numbers we have seen. Then we have seen that how we can optimize the circuit more to in terms of or in order to get the benefit of area and power consumption. Okay. So, that we have seen in the last class. So, again another type of circuit implementation, if I just want to implement, that is, suppose if I just want to do there what I need sum of n natural numbers. Now, if I need product of n natural numbers, that means if my S equals to 1 star 2 star 3 star to n. So, if I want to implement this kind of function, so at the time how can I do? If you see that it is something like same, that means here also n minus 1 number of multiplication I need, okay, for parallel implementation, or if I just want to compute it within 1 clock cycles. So, if the n increases, if n is, let us consider 16. So, at that time I need 15 number of multiplier. Okay. So, if I increase the n to a higher values, so this value will also increase, and as we know that this value of, that means the corresponding hardware cost for multiplier design, that is on the higher side, and for that reason there are several works or several architecture for getting the reduced hardware, or in terms of high speed, or in terms of low power multiplier architecture, or people have, or there is a, that means very in depth research on this particular multiplier architecture, where I can get this, that means these three things, where speed as major concern, or area as major concern, or this power as a major concern. So, we will come to that particular architecture, what are the, that means architectures available for multiplier designing in corresponds to this speed, power and area, that we will see later of this course. Okay. So, one particular module is only for this multiplier design. So, that is not a part of at this point of this course. Okay. But the thing is that from this particular point, it is just the message that multiplier is basically a that means a circuit which cost a more area. So, that means the more number of multiplier we use, more the area and power we consume for that particular circuit. Okay. So, that is why we have to that means avoid, or we have to reduce the number of multiplier architecture in a particular system or in a particular function implementation, so that I can get the benefit of area as well as this power. So, how can I do that? Here also the same thing, same logic, whatever we have done in case of sum of n natural numbers. So, here only the change is that, so here the logic will be same. So, the only logic will be that I equals to 1 to n, S equals to A star I. So, initially you can start with this logic, or you can start with the same logic, I equals to n to 1, S equals to A star I. Okay. So, the same thing here you can do, and here in this particular case another change you require, that was in the sum of n natural numbers, initially what we have done, this S register is set to 0. So, initially S equals to set to 0 for whenever we are finding the sum of n natural numbers. But here if you just consider this is I and this is basically multiplied here. So, initially if you set to 0, whatever cycles or how many cycles you do, once you set to this to 0, that means in again this will come to this. So, that means 0 will be computed in each of these particular cycles. So, you do not have to set to 0 initially for this particular S registers. Here initially it will be set to 1. So, there the initial signal that was clear for some, but here this will not be clear, this will be preset to, that means this register's value initially it will be 1. So, 1 and then whatever value is initially coming from this, that will be I. Okay. So, that is the only change, otherwise the rest of the circuit will remain unchanged, it will be same as the sum of n natural numbers. That means, if I just draw the circuit, so here this is the multiplier, again this is the S, this is the I. Okay. So, then again it is coming to here and I is coming here, then I is basically connected to this and here what I require, okay, and I need what? I need another control signal for this. This is the initial signal. Here it will be preset, okay, and this is the circuit for product of n natural numbers. Okay. So, you see here what I require only one multiplier, but the problem with this sequential implementation, in the last class also we have discussed, that means whatever the value of that means this is the n. So, whatever the value of n is, I have to wait for n minus 1 clock cycles. So, that means the total computation time for this particular circuit, suppose if that means minimum clock period is, let us consider 2 nanosecond, okay, and n value is, let us consider 128. Okay. So, that means 127 into 2, that is 4 and 254 nanosecond I require as a computation time for this particular circuit. That means, I have to wait for 254 nanosecond to produce the results after applying the input over here, or the starting of this total computation. Okay. So, if you have that liberty in the corresponding, actually it depends on the application where you are, for which application you are designing the corresponding functions or corresponding this expressions. So, if in one particular system you have the liberty that you can wait for 254 nanoseconds, so at that time you can go for this particular implementation. But in some case, suppose in a critical case, this kind of architecture you require where you cannot wait. So, that means time is a that means very much critical condition. So, at that time you cannot wait for 254 nanoseconds. So, at that time if I just implement this particular logic using this n minus 1 number of multiplier. So, at that time what will happen? So, that can cost me, suppose this is the multiplier 1 multiplier or this total 2 nanoseconds. So, n minus 1 number of multiplier I require, and log 2 base n, that is the that means number of stages I require for implementing the parallel implementation. Why? Because if I am having 8 number, I have to add. So, at that time I will have log 2 base 8 means 3 stages, right, of adder or 3 stages of multiplier. So, here if as I have chosen this n equals to 128, 128 means that is 5, 6, okay. No, 2 to the power 5, 6, 7, sorry 7, okay. So, that means 7 stage will be there. So, in each stage if I consider for each of the multiplier it requires 2 nanosecond. So, that means total 14 nanosecond will be the time requirement for parallel implementation of this. So, hardware wise this is reduced, but that means 14 nanosecond it is required means after applying the input once, after 14 nanosecond I will get the output, but here I have to wait for 254 nanosecond. So, that means in one particular case where I require the time as the critical one. So, at that time I have to go for this, I have to that means allow that okay it will consume more area, but I can save the time here, and in terms of actually if I say it in terms of here I am purchasing the time with the cost of area, and here I am purchasing the area in terms of this time. So, these are the two different implementation technique for one particular architecture or one particular circuit implementation. Okay. So, this is sum of product of n natural numbers. Then again we will see one another architecture or another function if I want to implement, then how we can start with, and then how can we build the architecture for that we will see next. Suppose I have to design one GCD function. Okay. GCD function means greatest common divisor among two numbers. So, I have to find out GCD of, let us consider m and n. So, I think this is the basic mathematical operation we have learned in our that means in our high school days. So, GCD of m and n means suppose I am having two numbers. Okay. So, 20 and let us consider 30. Okay. So, initially how we can find out? 2, here 10, and then this is 50, then here 2, this is 5, this is 15, then 5, here 1, and here it is 3. Okay. So, then what is that means common term over here? So, 5 is common in both the cases and 2 is common for both the cases. So, that means here or else if I just write it 20 equals to 2 into 5, that means 4 into 5, and 30 if I just write it something like this, 2 into 3 into 5, then what are the common factors among these two numbers? That are 2 and 5. So, that means the GCD value is 2 and 5, that is equals to 10. So, 10 is the number which basically the greatest number which can divide this 20 as well as 30. So, I have to implement the circuit corresponding, which will give me, I will put the values of m and n. So, it will give me or it will produce me the GCD of that. So, how can I do that? So, for that I need to follow the modified Euler's algorithm. Okay. So, according to the modified Euler's algorithm, so it says that whenever this I am having two numbers m and n, okay, when this is m is even and n is also even. So, at that time m will be m by 2, n will be n by 2. This is the input and this is the, that means in each stage how the out, that means value will change for m and n. If this is even and this is odd, then this will be m by 2 and this will remain unchanged, n will be same as n. If this is odd and this is even, so at that time it will be m and this will be n by 2, and both are odd. So, at that time what will happen? This will be minimum of m and n and this will be mod of m minus n. So, this is the algorithm for finding out the GCD. So, then we see, if we see, okay, that let us consider the previous case 20 and 30. So, in both this case what will happen? Twenty and 30 means both are even. So, in the next it will be by 2 by 2. So, here it will be 10, here it will be 15, sorry, here if I just write in the next, here it will be 10 and 15. So, then here if it is even, this is odd. Okay. So, in the next what will happen? This will be 5 and this will be 15. Okay. Then both are odd, both are odd means then this will be minimum of m and n. So, among m and n minimum is 5 and mod of m minus n is, here it is 10. So, then again this is even, sorry, this is odd, this is even. So, that means 5 and here this will be 5, and when both the numbers are same, at that time the computation will be over. So, that means as I find that, okay, m and n, sorry, both are same. So, at that time there will be no other computation. So, now according to this, what I said that when both the numbers are even, at that time only it will be multiplied with 2, the output values that will be multiplied with 2. Okay, output values means finally whatever, that means remainder is coming over here. So, that will be multiplied with this 2 for finding each of this even case. Means what? Here how many times we are finding this even case? Only for this particular case. So, that means only once I have to multiply it with this particular value. Here for 5 and 5 this value is same. So, that means, and how many times I am finding out even and even? That is only one time. So, that means this will be multiplied with 2 and I will get the results of 10. Now, let us consider another case where I can find more of this. Okay. So, that means now if I consider another example of that. So, that means here if I consider 40 and let us consider this as 60. Okay. So, that means for this particular case initially it will be 20 and 30, then 10, 15, then something 5, something like this. So, 20, 30 means it will remain like same. So, for this particular case I am finding what? I am finding both are even. So, this is already stored one times. So, again I am finding both are even. So, that means now it will be 1 plus 1. So, that means 2. So, 2 into 5, that is equals to 20 is the greatest common divisor among these two. If you see 40 and 60, the common divisor among them is 20. Okay. So, that means using this particular logic or this particular things, I can get the GCD function of two numbers which is m and n. Now, this is the logic. Okay. So, this is the algorithm description of finding out the GCD function of two numbers based on this particular algorithm. Now, I have to implement this as a circuit or architecture for this particular algorithm. How can I do that? Or where from I have to start with. Okay. So, for that reason what I have to do, initially I have to make the corresponding operation table. Okay. Sorry. So, operation table means it is just same as this. So, m and n. So, if this is even and this is for odd case, this is for even and this is for odd case. Okay. Whenever m and n both are even, so at that time what happens? M, that value equals to m by 2 and n, that is equals to n by 2. When m is odd, n is even, so at that time m equals to m and n equals to n by 2. When this n is odd, m is even, so at that time m equals to m by 2 and n equals to n. When both are odd, so at that time m equals to minimum of m and n, and n is mod of m minus n. Okay. So, this is the operation table for this particular algorithm, right. So, that means what I need to do? I need to, if I just plot it, that means I need to know about, that means what are the signals or how do I define that okay m and n value is even or odd? How can I know? If you see the LSB of m or n, LSB of any variables, if that is 1, that means that is the number is obviously that will be odd. If the LSB is 0, obviously the number will be even in binary number of system. Why? Because at the LSB, suppose if I consider 2 bit, and how can I find the decimal number? That is weighted basically representation. Suppose 2 bit if I consider, that is 2 to the power 1 into a I plus 2 to the power 0 into a 0. Okay. So, if a 0 bit is 0 means what? Sorry, this bit is 0 means this is here you will get 0 and whatever, suppose this is 1. So, you will get 2. If this bit is 1 and 2 to the power 0 means 1. So, obviously, you will get 1. So, it will be 2 plus 1, that is equals to 3. So, that means now from that particular point I can say if this bit is 0, obviously, it will be even. If this bit is 1, so 1 will be added to the whatever number is there. So, that will become odd. Okay. So, that means for that reason, if I consider only the LSB of m and LSB of n for calculating this even and odd values, I can, that means this now this LSB of m and LSB of n, that will be the control signal for what operation I need at what point of time. That means, this will give me, this will indicate okay, that this is the even number or m is even or m is odd. So, we will find out based on these two particular function LSB of m and n. So, that means, this will be the control signal which will produce the corresponding functionality changes in each of the cycle. Okay. So, that means, I require this initial signal LSB of m and LSB of n. Okay. Here, but this is a function. So, initially what will happen? Initially, this is whenever I have to initialize. So, that means, at that time m will be loaded to m next and n will be loaded to n next, sorry, n next. Okay. So, this is for 1 cross 1 case. Whenever this is 0 and this LSB of m equals to 1 and this is 0, LSB n equals to 0. So, at that time what will happen? M equals to what? M and n equals to n by 2. Then again 0, this is 0, this will be 0 and 1, m equals to m by 2, n equals to n, and for 0, 1 case, this is sorry m equals to minimum of m and n and n equals to mod of m minus n. Okay. And for both the case, for 0 0, it will be m will be m by 2, n will be n by 2. Okay. For 0 0 0, m equals to m by 2 and n equals to n by 2. So, for m equals to m means what? Basically, it will that means the input and output will be same. That means, here Q I will be the Q I value. Okay. And whenever this by 2 means what? Q I will be Q I plus 1. That means, just discard the LSB position. Okay. And then this I require as the other input or other function. This I need the, that means other circuitry to produce the minimum for m and n and mod of m minus n. Okay. So, this is the operation table. Now, it is the same way how we basically do earlier case. we have find out the operation table. So, from that operation table we have got the truth table. So, this is something like truth table. So, from that truth table now we will try to find out the expression. So, from that expression will be converted to the architecture. So, for today this is it. Then again in the next class we will continue with this particular example. Thank you.